Today we're going to look at how to train artificial neural networks, just starting with simple architectures using TensorFlow. I'm going to give a brief revision on basic algebra operations that we're going to use, and then talk a bit about how TensorFlow works at the lower level, the computational graph, the way auto-differentiation is computed to allow us to do backpropagation, and then how training with stochastic gradient descent can be optimized, and some variants on how to do this training. And then after the break, we're going to start with TensorFlow and looking at how to actually implement these things and get them to work. So let's start with a brief revision of some basic concepts. In algebra, when we talk about a scalar, this is just a number, basically. A vector is an ordered array of numbers, and then we usually talk about a matrix, which is a two-dimensional array of numbers. In TensorFlow, we're going to be dealing with tensors, and this is a more abstract concept, which is basically formally a relation between sets of algebraic objects, but for our purposes, we can think of a tensor as an n-dimensional array. It can have 2, 3, 4 dimensions, whatever we need, and this will be the basic blocks that we'll be operating with in TensorFlow. And this is why it's called TensorFlow, because we are moving tensors along the computation graph when we are training the network and doing the predictions and so forth. So in algebra, we can easily add or subtract tensors, so a matrix of any number of dimensions, as long as both tensors have the same dimensions. So they have the same number of dimensions and the same length in the corresponding dimensions. So adding and subtracting is done just element-wise. If we have a matrix A here with these values and a matrix B here with these values, and they have the same number of columns and the same number of rows, we obtain this matrix resulting from the sum of the other two simply by adding the corresponding elements. The same thing for subtraction. So this is simple. When we are doing matrix multiplication, in 2 dimensions, if we are using this algebra rule of multiplication, the operation is a bit trickier. First, if we are multiplying matrix A by matrix B, we need to have the same number of columns in matrix A as we have of rows in matrix B. And this is because we are going to, for each value in the resulting matrix C, we are going to compute the product of the first element here of the first row of A multiplied by the first element of the first column of B, and then add the second element of the row multiplied by the second element of the column, and so on, to get this first value. And then we keep repeating this for each row of A and each column of B, and we do this operation in order to compute all the values of matrix C. So this is the basic rule of matrix multiplication in algebra. I'm sure you already know this, so just to remind you. And the reason why this is very useful and relevant for artificial neural networks is that we are basically doing this kind of operation, multiplying some vector of inputs by a vector of weights, and adding everything up together to get one value. So you can see that at each step, this is what we're doing. If we imagine this to be a matrix with all our examples, and this would be a matrix representing all the neurons at some layer, we would have here the net values of all the neurons for all the examples computed with one matrix multiplication between these matrices. So basically, we can pass a set of examples through a layer of neurons and obtain the output of all the neurons for all the examples with one multiplication of the matrices, and then applying the activation function to the values in this matrix. So this way we are doing all of these sums of products and then applying the activation function afterwards. So this is basically the idea, that we can follow the basic blocks, so to speak, to do these operations with neurons, where we do matrix multiplication and then apply the activation function. TensorFlow, like NumPy, also allows broadcasting. So we could do multiplication by other rules than, for example, the basic algebra multiplication, or sums or things like that. As long as TensorFlow can match the length of the last dimension of one matrix and the other. So, for example, the number of columns in this matrix A must be the same as the number of elements in vector B. If it can do that, it can align the last dimension and then simply broadcast or replicate the operation through all the other dimensions. So in this case, it would repeat for each row of A this element-wise sum with all the values of vector B. So we can combine these two different types of operations, so the actual algebra multiplication of matrices and broadcasting, and broadcast these multiplications over batches of matrices. With the matrix multiplication function, this matmul function in TensorFlow, we can multiply algebraically matrices that are in batches in higher dimensional arrays. The rule for this is that the last two dimensions in our arrays must correspond to a pair of two-dimensional matrices that we can multiply. For example, in this case, we have an array that has two matrices of 2 rows by 3 columns. And this other array B, this tensor B, has two matrices that have 3 rows by 2 columns. Since we can multiply a matrix of 2 rows by 3 columns with a matrix of 3 rows by 2 columns, we can use matmul to broadcast these products, these matrix multiplications, over the whole set of matrices. That is, over all these tensors. And what we get here would be the algebraic product of matrix A and B using the first matrix on the tensor A and the first matrix on the tensor B, and then the same thing using the second matrix. So basically with TensorFlow we can combine broadcasting with matrix multiplication, and this way we can do in single steps, passing through lots of elements through our layers, for example, or computing the output of different layers and so on. So this is basically what makes it easy then to do all the computations necessary to predict or to train these neural networks. Okay, so the reason why I'm telling you this is that our models, our artificial neural networks, will be based on these types of operations. Typically, we will have batches of examples that will be tensors. If each example has just a vector of features, then a batch of examples will be a two-dimensional tensor. For example, each example in a row and each feature in a column, like a small table of examples. If our examples are more complex, for example, if they are images, they can have multiple dimensions, and we can have batches of 3 dimensions or 4 dimensions, depending on the number of colors we have on the images. So these tensors can be of higher dimensions, but we can work with these tensors and pass them through all these operations, and the layers of the networks will work as matrix multiplications through the weights of the neurons, and then the application of those activation functions to the product of those multiplications, and so forth. Typically, our loss functions will then aggregate these values. For example, when we are computing a quadratic error, we will measure the square of the differences between the values and then sum everything together and do these kinds of aggregations. Now, in practice, and we'll start looking at this from next week onward, we will not worry too much about this level of detail, because we're going to use a programming interface, Keras, which allows us to define neural networks at a higher level, where we just specify what kinds of layers we want and how things fit together. And all of these detailed operations are hidden from view, encapsulated in those objects. However, it's important to start from here so that you can understand how TensorFlow is working deep down, and also because sometimes you may need to actually work at this level. For example, if you have to create a custom loss function or something like that, or a more or a stranger kind of connectivity between layers, something like that, then you may need to actually know how TensorFlow is doing this in order to go a bit beyond what the simplified interface allows you. So that would be the idea here for today. We're going to start with these simple elements, create some very rudimentary networks just by using these operations, and understand how TensorFlow is working. And then we're going to use Keras to move on to more sophisticated architectures. So let's start with the very simple example. We will have these inputs. They are two-dimensional, so we have two coordinates for each example. Each example is a point here. The points are divided into two classes, and our network just has these two weights here. One weight corresponding to one of the coordinates, and the other corresponding to the other of the coordinates. Then we have the sum here, and we have a sigmoid activation for the output of our pseudo neurons, because this is not even a proper neuron. It doesn't have the bias value, but this way, this is really the simplest we can do and do anything interesting with. And we have only two weights, so we can represent graphically in 2 dimensions how these weights are, what are the results of having different combinations of these weights. So let's start with this very simple example. And the way we can compute the activations for a batch of points here is we can consider that we have a matrix that has in each row the coordinates of each of these examples. And the two columns are the two coordinates. The first column is x1, the second column is x2. If we now store the weights of this simplified neuron here, the two weights corresponding to these arrows, if we arrows store them in a column matrix, then we can use matrix multiplication to obtain the sum of the product of the weight and the corresponding input for all our examples. Because for the first row here, we will have x1 of the first example multiplied by weight 1, added with coordinate 2 of the first example multiplied by weight 2. And then we add these together and we will obtain this result for the first example. Then the same thing for the second example, for the third, and so forth. So this way, by using matrix multiplication, we obtain these sums, and then we can apply the sigmoid activation function to the column matrix that we obtain here and obtain the output for all our examples. So this allows us to, with one operation and applying the sigmoid activation, obtain the activations of our network for a batch of examples. Now we need to adjust the weights. So it's not just about computing how the network fires, what is the activation, but also computing the derivatives in order to do backpropagation. So remember, since we only have one neuron here, what we need is for each weight, we need to estimate the gradient of the error function, the loss function that we're using, with respect to that weight. But to do that, to go from the error to the weight we are updating, we need to chain through all the different functions. The error function as a function of the output of the neuron, the output of the neuron because of the activation function as a function of that weighted sum of the inputs, and then the weighted sum of the inputs as a function of that particular weight. If we had more layers, then we would have to backpropagate this through the network. In this particular example, we are just looking at one neuron, but in any case, we also always need to do this. We need to do this kind of gradient computation or differentiation in order to be able to know how to update each weight. So backpropagation is a special kind of reverse mode automatic differentiation where we start from the end and trace back to the beginning, so to speak, and we chain all the different derivatives. So just to give you a bit of a broader view of how we can solve these problems of differentiation, one way of doing this is doing it symbolically. That is, we compute symbolically the derivatives and we obtain an expression for the resulting derivative for our particular problem. So this could be what we were doing here. We would obtain an expression that would allow us to compute the derivative of the error function with respect to some particular weight at some particular neuron. However, there is a drawback to this, because doing symbolic differentiation, computing the actual expression for all the chained derivatives, will vary a lot depending on how we fit the neurons together, what are the activation functions, what is the loss function, and so forth. So it's not practical to do this for any neural network, because then the expressions change a lot between different architectures. It's also something that does not work well with flow control elements. If we have conditions or loops or things like that, then computing a single expression that takes into account all the different cases is very hard, and it's really, it complicates a lot this kind of approach. So this is not the approach we're going to take when trying to do backpropagation with TensorFlow. Another possible approach is doing numerical differentiation. In this case, what we do is we compute different small steps for our function, and we estimate the derivatives by looking at the differences of the output values when we do these small steps. So we do increments of a small delta and estimate the derivative from there. This is not very good because not only it requires a lot of computations, we have to use very small deltas, and if we use very small steps, this can take a long time to get us to where we want. But if we use steps that are larger, then generally we have convergence problems and things blow up. So it's not at all feasible to do backpropagation with numerical differentiation with neural networks. So what TensorFlow does is called automatic differentiation. And the way this works is by applying the chain rule, so these products of all the derivatives, to elementary operations for which we know how to compute the derivative. So if we know what is the derivative of the quadratic error, for example, or the square, or the difference, or things like that, we can compute precisely not only the value of the function at some point, but also the value of the derivative of that function at that point. And using that, we can chain together the different different derivatives in order to do backpropagation, in order to do differentiation in a more general case. So you can see here what happens with TensorFlow if we want, for example, to find the value of x that minimizes cosine of x. To do this minimization, we need the derivative of the cosine of x as a function of x in order to figure out where to slide down when trying to minimize this. But we know that the derivative of the cosine function is minus the sine of x. So this is something that we know analytically. We'll use this basic operation, cosine, we know how to differentiate it. And so, in that case, what happens is that TensorFlow will associate to the function cosine that we have here in the computational graph, we'll associate the computation of the gradient for that function, and the gradient for that function will be minus the sine of x. I have here a bit increased the magnification. So we have the sine function, the negative, we multiply the minus sign with the sine function, and this is the derivative, the gradient of the cosine function. So this means that when TensorFlow is doing these computations, when it is evaluating the cosine of x for any particular x, it will also evaluate the gradient for that particular x. So it keeps both numbers, it keeps tracks of both numbers, and this is called a dual number representation, and it operates on those numbers. and the kinds of operations we are going to do with the value of the cosine of x, for example, it will also do with the derivative of the function, and that way it will chain together the derivatives in parallel with the computation of the values of the functions. So this is how TensorFlow keeps track of all the gradients in order to do these optimizations. For example, if we want to find the minimum, the value of x that minimizes this expression, x squared cosine of x plus sine of x, associated with this expression, we have these gradients which include the derivative of the sine function, the derivative of the cosine function, and then the sum, the multiplication, and so on. So all of these are chained together in order to keep track of the gradient of our function as we compute the graph for these computations. Okay, so now let's go back to our simple model and see, still a bit abstractly, how we can now train the model and adjust these weights in order to best separate between the two classes. So what we are going to do is to use stochastic gradient descent. We start at some random point in our combinations of values. So here you can see in these two axes we have one of the weights and the other weight. And now we are sliding down the error function because at each point we know the gradient and we can compute the direction where to change the values of our weights. And as we slide down the error function, the discriminant between the two classes will now change as these weights are changing, and we start to improve the classification. That is, we start to minimize the error. And this is stochastic gradient descent because at each point here we are presenting our examples in random order, and we are using the examples to estimate the gradient of the error function. Note that in truth, what we mean by the gradient of the error function would be the average error over all the data. We are estimating at each mini-batch, at each iteration here, we are estimating that gradient using a sample of the data. But then I'm representing here passes through all the epochs as we slide down the error function. So now, how can we do this? There are several different ways I'm going to talk about today. I'm going to talk about a few more sophisticated ones later on in the course, but we can start with a very basic approach here. We have this gradient descent because we are sliding down the gradient, so we just need to compute the derivative at this point. And this is a bit stochastic because we are choosing examples at random and we are estimating these derivatives from this random sample of examples. And the estimate would be something like this. We have this loss function. So in our case, it could be, for example, the quadratic error between the output of the network and the class we want to assign to each point, or it could be the logistic loss, something like that, like we use in logistic regression. But in any case, we have this loss function that we want to minimize, and this is a function of what our network is outputting. So our network, given some set of features x and the parameters for the network, all the weights, will output some value, and comparing this value with the target that we want the network to predict correctly, so the actual labels of our points, this will give us the loss function that we're trying to minimize. What we are doing is we are estimating the gradient at some set of parameters. So this is what I'm representing here. These coordinates are the two weights of our simplified neuron. So at each point, we have a combination of parameters for our network. And we are estimating the gradient there by using a sample of points. So basically, we are averaging the loss function over a subset of points, these m points that we selected. And then we estimate the gradient at this combination of parameters. And now we update all the parameters by sliding down a bit in the direction of the negative of the gradient. So we use here a small value, this learning rate, to multiply the gradient estimate, and we subtract that from the vector of parameters that we had before, and this will give us the next set of parameters. So this is what we are doing here in gradient descent. We are estimating the gradient for a combination of values and then moving down, changing the values of the parameters, and doing this again and again and again, and sliding down the error function in this way. Okay, so this would be the basic stochastic gradient descent. But there is something we can do to improve here, because sometimes we are finding that consecutive iterations are always moving in the same direction. We are sliding down this ravine here, for example, and we are looking always at the same approximate direction when we are moving in this stretch of points. So what we can do is to use what is called momentum. Instead of using the gradient as the value we want to use for updating our weights, we are going to use the gradient to change the velocity with which we are moving in a particular direction. So the velocity at the next iteration will be a fraction of the velocity on the previous iteration, and the velocity is actually a vector that indicates where we were going here in this sliding down. And we are going to change this by adding the negative of the gradient estimated in our batch of points. So what happens here is that if we keep moving in the same direction, these things will keep adding up and the velocity will start increasing. If we suddenly have to change direction, then they will be a bit contradicting each other, and we will have a slowing down of this process here. So Carolina asked if we use the usual value of 0.1 for the learning rate. This depends a lot on the actual problem and the network and so on. Typically, if you have large networks, 0.1 can be too high, and you can have problems at the end with convergence and so forth. But I'm going to talk a bit more about that today, and we're going to look at that in more detail further on, because generally it's a good idea to use different learning rates during different stages of training. Start with a higher learning rate, and then as we start reaching a point where we are fine-tuning the network, we can start reducing the learning rate in order to avoid oscillations and to improve convergence. But we'll talk a bit more about that in some future classes. So this way, if we use momentum, we can accelerate when we are moving in the same direction. And so if we can compare the two, this is stochastic gradient descent without momentum, and this is with momentum. So if you can see right at the beginning, since the change is always in the same direction, using 0.9 momentum, this is the parameter here, the fraction of the previous velocity we are keeping. If we do that, we can quickly slide down this hillside here until we reach the turn, and then things slow a bit, but then they accelerate again. If we just use stochastic gradient descent, we take a long time because we're always taking small steps, whereas with momentum we keep accelerating and taking advantage of the fact that we are moving always in the same direction. So typically using momentum can be of very great help in training neural networks. It makes things a lot faster. One improvement that we can use, this is called Nesterov momentum, is that instead of computing the gradient or estimating the gradient in the place where we are now, so we're using this combination of weights in our neural network, we can consider what the gradient will be if we take this step first. So since we are using momentum and we already have some velocity, if we take first this step and then compute the gradient, maybe we can have more information about what the real gradient is. And this is the idea of Nesterov momentum. Instead of estimating the gradient exactly at theta, at this set of parameters, we are actually looking ahead and seeing what the gradient will be if we take this step first. Now, this is very good for optimizing convex functions, and this is Nesterov momentum is used in some optimization problems, and it improves a lot the convergence rate because we have this information about where we will be next, and it gives us a better estimate than using the point where we are at now. Unfortunately, when we use stochastic gradient descent, these gradient estimates are very approximate and they change a lot. They are subject to a lot of noise because of the random sampling of those batches of examples that we are using. So in practice, Nesterov momentum doesn't work as well when training neural networks. So if we can compare, the Nesterov momentum with just the basic momentum, we don't see any difference between the two. So looking ahead after the velocity and estimating the gradient there does not give us much information in practice in general for artificial neural networks because our estimates are stochastic based on a sample of points. However, it's important to note that the example I'm giving here is really not realistic. We don't use neural networks with just two parameters. Unfortunately, if we have a neural network with, say, 100,000 parameters, we cannot plot these charts in any way that we can understand. So I have to use a very simple example to illustrate this. But the basic message is that Nesterov momentum usually doesn't make much difference, but you should, if you want to really fine-tune the way you're training your network, you should experiment a bit with this because this depends a lot on the kind of network that you have, the size of the network, the problem, and it can change from problem to problem. So you can always experiment and see if you see some improvement in the training of your network. Another parameter that we have to consider is the size of the mini batch that we're using, that batch of examples we're using to estimate the gradient. Now, averaging over a large set of examples, the larger it is, the better the estimate of the gradient. So the true gradient would be computed for all the data that we have. If we are using a subset of the data, the larger the subset, the more accurate will be the estimate of the gradient of the loss function. However, if we use smaller mini batches, we are improving generalization because of the randomness factor. We are using this randomness here. It can help us avoid some problems with overfitting. For example, it can help select or find the best path down the error function and so forth. So there is a bit of a trade-off here on the benefits of using larger batches or the benefits of making this gradient descent more random with smaller batches. Usually the practical limitation tends to be the available memory, especially if we are using GPU acceleration and we cannot put all our data on the memory of the graphic cards, for example. And this is also a reason, this kind of optimization is also a reason why you often find mini batches with a power of 2. For example, 8 examples, 16, 32, something like that, because this optimizes the way the GPU card can parallelize these computations. So basically, the big difference that we have in mini batches is that if we can use larger mini batches, usually we can speed up computation, but sometimes at the cost of lowering the randomness of the descent, and this may lead us to getting stuck or making the training less efficient. In this case, for example, comparing a mini batch of 10 points, so we are estimating the gradient with 10 points at the time, and then moving, and then estimating with 10 points and moving and so forth. And here the movement is done 1 point at a time. The representation that I'm drawing here with this line growing is done by epoch. So one epoch is one pass through all the examples that we have. So this seems to be working when we look at this by epoch. they seem to be working at the same rate, learning at the same rate. However, this one takes is a lot faster to compute because it's parallelizing these computations of 10 examples at a time and only updates the weights of the network after the 10 examples. So if we measure in time, this is faster than this one, and we are not losing much by grouping the examples in groups of 10. So typically mini batch sizes can be things like 16, 32, 64. You can go all the way to 256 or something like that. If you start making them too large, you are losing a bit the randomness here. But usually the limiting factor is how much memory you have available for the GPU, because you can really speed up the computations if you use larger batches. Okay, so now let's improve a bit the model, because this pseudo neuron is not even a proper neuron. It does not have the additional degree of freedom that you can have with a bias value. And we can think of this bias, this additional value that we add to the sum of the products of the inputs and the weights, as an additional weight that is free from any input. So you can imagine that it was just being multiplied by 1 all the time, and we can change it regardless of what the input is. So the big difference here, and the reason why we need this for the neurons, is that if we don't have this bias input, then when the input is 0, the output is always 0. Because if we have 0 on all the x's, whatever weights we have, this sum of products will always be 0. So you can see that without the bias vector, our discriminant is stuck somewhere here, like it's pinned at 0, 0 coordinates, and it cannot deviate from there. There is no way it can shift from there because it has no additional bias value. If we add the bias input, then it can oscillate as necessary for one side or the other. In this case, it doesn't change much, but we can see that it's a bit in a different position relative to the other. And in general, we need this additional freedom to adjust the transformation that each neuron is doing. So we always need this bias input to improve this freedom of the output of the neuron. Okay, but in any case, this data set, we cannot properly separate it with just one neuron. So let's look at a deeper network. We're going to use 2 hidden layers, each one composed of 2 neurons. We have one output layer for the classification. It tells us if it's red or blue. And we have these bias values for all the neurons that we use. So each neuron has this additional weight that we are free to change independent of the inputs. It does not get multiplied by the input. So this is a representation of what's happening in this network. Here below we have the original data that is being input, and then we have the transformation that is being done on the first hidden layer. So the values I'm plotting here at this layer are the output values of these 2 neurons. And as you can see, as the network is training, these neurons start to reshape the data in a different way. And then they are being fed into the second hidden layer. And this is what I'm representing here at the top of the chart. So this layer transforms it this way, the second hidden layer transforms it this way, and the output neuron is only looking at these values. So this is the original data, but this is what the output neuron, which is the linear classifier, is looking at when it's predicting the class of each point. And when we project back the discriminant, the linear discriminant, the output neuron is creating here, if we project it back through these nonlinear transformations, we get this frontier here between our points that we can see starts to become twisted and have these curves in order to improve the classification of the points. So this is just an illustration of what's happening inside the neural network as the neural network learns to transform the data appropriately. Okay, so some things that are important here. We need to initialize our network with some random values, because we need to break symmetry between the neurons. Note that we are going to use these expressions, these activations, to compute the derivatives and use those derivatives to update the weights. So if we have two neurons that are exactly the same, they have the same weights, then their derivatives will always be the same and they will be updated always exactly the same. So those two neurons will always be the same. If we start everything with the same value, then all our network will be composed of neurons of always the same weight, and this will not work because they will always be synchronized and we will not be able to do anything with them. So it's important to use random values, preferably close to 0, so that we don't saturate our output functions immediately. Because, for example, with a function like this, a sigmoid, if we move away from 0, we reach these saturation values, and then the gradient starts to become very small. So we need to start somewhere in this region where we have more information about how to change the weights. These values, the bias values, they can start all at 0 because they are not important for breaking symmetry. So these extra values here, we can just set them at 0. But the weights for the neurons is important that they are all different, and so we choose them at random. We can use Gaussian distributions, uniform distributions, or actually there are more sophisticated methods we're going to look a bit in more detail further on. But basically, the important message now is that we cannot have neurons that start with the same weights, because those neurons will always have the same weights if they are in the same layer, and that will ruin the network. Another thing is that we are doing stochastic gradient descent, and with random initialization of the weights, which means that our trajectories will not be exactly the same when we run things twice. So usually we should run, if we can run things a few times to experiment, or at least allow enough time to run, because convergence may come later or sooner depending on how lucky we are in each of these trajectories. It's also important to standardize the inputs, because it makes it easier for the network to adjust, especially when we are using these more basic optimizers that use the same learning rate for all the weights. So if we are using the same learning rate for all the weights, but some inputs are scaled differently from others, then we have this problem that the learning rate may be too fast in one case for some weights and too slow for other weights, and things don't match very well together. So it's always useful to put everything at the same scale, avoiding the combination of very large and very tiny values, also because of numerical problems, and shifting the mean of the inputs to 0 and setting all the dimensions at the same scale makes it easier for the network to learn. Now, this is just a note on nomenclature. We call one epoch one full pass through the training data. So we're going to present all the data points to our network, and we usually do that in mini batches, in groups of points, for example 8, 16, something like that. And in general, we need many epochs to train. Unless we have a huge data set, we need to present our data several times to the network until it starts to converge. So what we usually do is, for each epoch, we present the data in some random order in batches, and then we restart with a new epoch and so forth. So it's important to shuffle the data between epochs, because if we present the data always in the same order, we may start getting some strange patterns like this, where things go back and forth, something like that, because we are moving around in circles, for example, in the gradient descent, by showing always those examples in the same order. It's also important to take care with the learning rate, because if the learning rate is too small, we take too long to train. But if the learning rate is too large, then at the end we may have a poor convergence here, and we have some oscillations because the network cannot find the right spot. It is overstepping that and going back and forth and it's hard to converge there. So usually what is done in practice is to schedule the learning rate in order for it to start larger and then shrinking and shrinking along the training until when we are reaching convergence, the learning rate can be very small, and it's just fine-tuning the network. Okay, so this was just a bit in abstract to give you the broad ideas of what we need to do. We saw a brief revision of algebra, matrix algebra, because we're going to use that for computing the activations of the network. Automatic differentiation, this method that TensorFlow uses, keeping track both of the values of the function at some x and the values of the derivatives at that point too, and that is used then to do backpropagation by chaining together all those derivatives. Now we again saw these, the use of these layers, the nonlinear transformation, and looking at this special case of a multi-layer perceptron. So this kind of network where we have very well separated layers and all fully connected in the same direction, and each layer connected to the next, and so on. This is a very used architecture, but a very basic, very simple one. So we saw with this example, and we're going to practice a bit with this special case. So to read a bit more about optimization and these revisions for algebra, I would recommend taking a look at these chapters of deep learning. And we'll now take a short break. So we'll continue at 5 minutes before 5 with the second part, where I'll show you how to actually do this in practice in TensorFlow. So see you soon.